Sunlight may look like a continuous beam, but it is actually made of countless tiny packets of energy called photons. These photons travel from the sun, cross roughly 150 million kilometers of space, pass through Earth's atmosphere, and eventually strike the surface of a solar panel. A solar panel does not collect sunlight in the same way that a container collects water. Instead, it uses the energy carried by photons to set electrons in motion. That movement of electrons is what we call electric current. To understand how this happens, we first need to look at the material inside a solar cell. Most solar cells are made primarily from silicon. Silicon is one of the most abundant elements in Earth's crust, and it is found in materials such as sand and quartz. However, ordinary sand cannot simply be placed inside a solar panel. The silicon must be extracted, purified, melted, and carefully formed into solid crystals. These crystals are sliced into extremely thin pieces called wafers. A wafer forms the basic foundation of an individual solar cell. Silicon is useful because it is a semiconductor. A semiconductor is a material that sits somewhere between a conductor and an insulator. A conductor, such as copper, allows electric charge to move through it easily. An insulator, such as rubber, strongly resists that movement. Silicon can behave in either direction depending on how it is prepared. This gives engineers a way to control the movement of electrons instead of allowing them to travel randomly. A pure silicon atom has 4 electrons in its outer shell. Inside a solid silicon crystal, each atom shares these electrons with neighboring atoms. The result is a stable, repeating structure in which most electrons are held in place by chemical bonds. By itself, this pure silicon structure is not especially useful for producing electricity. To change its electrical behavior, manufacturers add extremely small amounts of other elements. This process is called doping. One layer of silicon is commonly doped with phosphorus. A phosphorus atom has 5 electrons in its outer shell, which is 1 more than silicon. When phosphorus is added to the crystal, 4 of its outer electrons form bonds with nearby silicon atoms, while the 5th electron remains more loosely attached. This produces a layer containing additional mobile electrons. Because electrons carry a negative electric charge, this layer is known as N-type silicon. A second layer is commonly doped with boron. Boron has only 3 electrons in its outer shell, which is 1 fewer than silicon. When boron is added to the crystal, one of the usual bonds is left incomplete. This missing electron behaves like a positively charged space, known as a hole. The layer containing these holes is called p-type silicon. The most important part of a solar cell is created when the N-type and p-type layers are placed together. The boundary between them is called the p-n junction. Near this boundary, some of the free electrons from the N-type side move into holes on the p-type side. As electrons cross the boundary, they leave behind positively charged atoms in the N-type layer. At the same time, the p-type layer gains negatively charged atoms. This creates a region around the junction where mobile charges have largely canceled each other out. It is called the depletion region. More importantly, the separated positive and negative charges produce an internal electric field. This electric field acts like a one-way slope for charged particles. It encourages electrons to move towards the N-type side and holes to move towards the p-type side. This direction is essential because electricity is only useful when charge moves in an organized path. Now sunlight enters the process. When a photon strikes the silicon, it may transfer its energy to one of the electrons held inside the crystal structure. If the photon carries enough energy, the electron can break free from its bond. The freed electron leaves behind a hole. This creates what is called an electron-hole pair. Without the electric field at the p-n junction, the electron might quickly fall back into a nearby hole, and the absorbed energy would mostly be lost as heat. However, if the electron-hole pair forms close enough to the junction, the electric field separates the two charges. The electron is pushed towards the N-type layer, while the hole moves towards the p-type layer. The solar cell has now created a separation of charge, similar to the separation between the two terminals of a battery. Metal contacts are placed on the front and back of the solar cell. The front contact is usually arranged as a pattern of thin metal lines. These lines must collect electrons while blocking as little sunlight as possible. When an external wire connects the two sides of the cell, the separated electrons gain a complete route to travel through. They leave the N-type side, move through the metal contact, flow through the wire and any connected electrical device, and eventually return to the P-type side. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. As the electrons move through the external circuit, they can transfer energy to a load. The load might be a light, a motor, a battery charger, or part of an electrical grid. The solar cell does not permanently lose its electrons. After traveling through the circuit, the electrons return to the cell and fill available holes. As long as sunlight continues producing new electron-hole pairs, the process can continue. A single solar cell produces only a small voltage, usually well below 1 volt. It can provide useful current, but its individual output is too limited for most practical applications. To increase the voltage, many cells are connected in series. In a series connection, the positive side of one cell is connected to the negative side of the next. The voltages of the cells then add together. Several rows of connected solar cells are sealed inside a protective structure to create a solar module, usually called a solar panel. The cells are fragile, so the panel needs several protective layers. A sheet of toughened glass covers the front, allowing sunlight through while protecting the cells from rain, dust, hail, and physical damage. Beneath the glass, transparent encapsulating material holds the cells in place and helps prevent moisture from reaching them. A protective backsheet, or sometimes another layer of glass, covers the rear of the panel. An aluminum frame strengthens the edges and provides mounting points. A junction box on the back contains the electrical connections that carry power away from the panel. Many solar panels also contain bypass diodes. These components become important when part of a panel is shaded. Because cells are commonly connected in series, the same current must pass through each cell in a string. If one cell is heavily shaded, it can restrict the current produced by the other illuminated cells. A bypass diode provides an alternative route around a shaded section. This reduces the amount of power lost and helps protect the shaded cells from overheating. It does not completely eliminate the effect of shade, but it prevents one small shadow from disabling the entire panel. The electricity produced by a solar panel is direct current, or DC indirect current. Electric charge moves mainly in one direction. Batteries also supply direct current. Most homes and electrical grids, however, operate using alternating current, or AC in alternating current. The direction of charge flow repeatedly reverses. The inverter does more than simply reverse the current. It carefully controls the voltage, frequency, and timing of the output. In a grid-connected system, the inverter must synchronize the solar electricity with the electricity already moving through the grid. The inverter also tries to keep the panels operating near their most productive point. A solar panel's voltage and current change depending on sunlight intensity, temperature, shading, and the electrical load connected to it. For every set of conditions, there is a particular combination of voltage and current that produces the greatest amount of power. This is called the maximum power point. Modern inverters use a process known as maximum power point tracking. The inverter repeatedly adjusts the electrical conditions and measures the result, searching for the point where the panel delivers the most power available at that moment. The power produced by a solar panel depends strongly on the amount of sunlight reaching it. Under brighter sunlight, more photons strike the cells each second. This creates more electron-hole pairs and generally increases the available electric current. The angle of the panel also matters. A panel receives the most concentrated sunlight when the sun's rays strike its surface more directly. At a shallow angle, the same sunlight is spread across a larger area, so less energy reaches each part of the panel. Clouds reduce the amount of direct sunlight, but they do not always stop electricity production completely. Some sunlight passes through clouds, and some is scattered through the atmosphere. As a result, panels can still produce power on overcast days, although usually at a lower level. Temperature has a less obvious effect. Solar panels rely on sunlight, but that does not mean they work better when they become extremely hot. As the temperature of a silicon cell rises, its voltage usually falls. A bright but cool day can therefore be better for electrical efficiency than an equally bright and very hot day. The panel may receive plenty of solar energy in both cases, but the hotter cell converts a slightly smaller fraction of that energy into electricity. Not every photon produces usable electrical energy. Some photons have too little energy to free an electron and pass through the material without creating an electron-hole pair. Other photons carry more energy than the cell can use for this process. The excess energy is quickly converted into heat. Some light is also reflected from the panel's surface, and some freed electrons recombine with holes before they can reach the electrical contacts. There is also resistance in the silicon, the metal contacts, the wires, and the other components of the system. Each of these losses reduces the final electrical output. For these reasons, a solar panel cannot convert all incoming sunlight into electricity. Commercial panels convert only a portion of the solar energy that reaches them, while the rest is reflected, transmitted, or transformed into heat. Manufacturers improve performance in several ways. Anti-reflective coatings reduce the amount of light bouncing away from the cell. Textured surfaces encourage incoming light to reflect internally, giving it additional chances to be absorbed. Thinner metal contacts block less sunlight, while improved contact designs reduce electrical resistance. Some advanced cells also collect charge from both sides or use additional layers to reduce the loss of electrons at the surfaces. When several panels are connected, they form an array. The electricity from the array travels through cables to an inverter, and from there it can be used by the building. If the panels produce more power than the building requires, the extra electricity may be sent into the grid or stored in batteries. If the panels produce less than the building requires, the remaining power can be supplied by the grid, a battery, or another source. In a battery system, the solar electricity passes through power control equipment before being stored as chemical energy. Later, the battery can convert that chemical energy back into electrical energy. This allows solar power collected during the day to be used at night or during periods of low sunlight. The complete process can now be followed from beginning to end. Photons arrive from the sun and transfer energy to electrons inside the silicon. The electrons break free and leave holes behind. The electric field at the p-n junction separates the electrons and holes before they recombine. Metal contacts collect the electrons and guide them through an external circuit. Many cells work together inside a panel, and many panels can work together inside an array. The resulting direct current travels to an inverter, which converts it into alternating current suitable for appliances and electrical grids. At every stage, some energy is lost, but the remaining energy becomes usable electrical power without burning fuel or requiring moving mechanical parts inside the panel. A solar panel is therefore not simply a surface that absorbs heat from the sun. It is a carefully engineered electrical device built around a controlled semiconductor junction. Its purpose is to separate electric charges, direct their movement, and give the energy of sunlight a practical path through a circuit. From a photon crossing space to an electron moving through a wire, the entire system is a sequence of energy transfers. Light energy becomes electrical energy, and that electrical energy can then become motion, illumination, stored energy, or power for almost any device connected to the system.